what if the exact same material needed to build the next generation of quantum computers was just, currently rotting in a pile of agricultural waste?
Yeah, it's a wild thought.
It really is. I want you to picture a very specific scene. Imagine you are standing on a coffee farm. You're in the Central Valley of Costa Rica, specifically in Cartago.
Right.
It's the rainy season. You are surrounded by these damp green mountains. The air is thick with heavy mist, and you're just looking down at the wet, muddy soil and the woody roots of an Arabica coffee shrub.
Okay, I can see it.
Now, take that rustic, earthy, deeply agricultural image, and I want you to crash it violently into the most hyper-sterile, freezing, unforgiving environment you can possibly imagine.
Right, so you're talking about the absolute vacuum of aerospace hardware.
Okay.
Or the intensely controlled, sterile environment of a quantum computing lab.
Exactly. That is the collision of worlds we are exploring today.
Hmm.
Our mission for this deep dive is to completely erase the border between rustic coffee farming and cutting-edge aerospace engineering.
It's quite a jump, I know.
It is. We are looking at the doctoral thesis of Martin Gutierrez Guerrero. He is the CEO of Nova Amazonia, which is a biotech and nanotech firm. And he's pioneered an innovation called 3D Biogy.
Yeah, the three-dimensional biogenic graphene.
Right. Derived entirely from discarded Arabica coffee plant waste. And, you should care about this because it isn't just some quirky botany project. We're looking at what appeared to be the master key to solving the most expensive, intractable bottlenecks in modern computing, heavy industry, and this is crazy, even human biology.
It really touches everything.
It does. Okay, let's unpack this, because to understand how a pile of discarded branches ends up processing quantum algorithms, we have to talk about the great historical disappointment of the tech industry, which is synthetic graphene.
Right. I mean, for the last 20 years or so, graphene was heavily marketed as the undisputed material of the future.
Oh, totally. The hype was everywhere.
It really was. And on paper, it's a miracle. It's a single layer of carbon atoms arranged in a hexagonal lattice.
Right.
It is the best conductor of heat and electricity, and structurally, it's the most resistant material we know of.
Right, on paper.
Exactly.
Oh.
But the reality of manufacturing it industrially has been, frankly, a massive letdown.
Because getting carbon atoms to lay perfectly flat, just one atom thick, isn't something nature just does on command for us?
No, not at all. It takes extreme brute force. So the industry standard right now is a process called chemical vapor deposition, or CVD.
Right.
And honestly, it is toxic, highly explosive, incredibly resource intensive.
Yeah, whenever I try to visualize the CVD method, it sounds like an absolute nightmare logistically. I mean, you have to pump these toxic carbon-heavy gases into a vacuum chamber.
Right.
Then you heat a metal plate, usually copper, I think to over 1,000 degrees Celsius. And the goal is to basically force the carbon atoms from the gas to rain down and deposit onto that blistering hot metal to form your atomic layer.
Yeah, and it's a colossal expenditure of energy just to create a single sheeted material.
Yeah.
But the real structural flaw happens after you manage to deposit that carbon.
Right.
Because now you have this impossibly thin, fragile layer of graphene physically bonded to a thick block of copper, and you have to get it off.
Which sounds like, I don't know, trying to peel a sticker off a window, except the sticker is only one atom thick and physically fused to the glass.
That is a highly accurate way to look at it, actually. As the chamber cools, the copper and the carbon contract at different rates, which immediately introduces physical stress.
Oh, sure.
Then, to actually separate them, manufacturers use highly corrosive chemicals to literally dissolve the copper away from the graphene.
Wow.
And that violent removal process is mechanically disastrous. When you try to rip a one-atom thick layer off a substrate, the material suffers microscopic rasgudoris, basically micro tears.
So the atoms essentially get misaligned and tangled up.
Yes, they lose that perfect, flat geometric structure. In material science, we call these sp3 hybridization defects. You end up with a microscopic mesh that is just riddled with tiny fissures.
Which completely compromises all those miracle properties we were promised, right? I mean, if the atomic mesh is torn, the electricity can't flow cleanly, and the strength is basically gone.
Exactly.
So to visualize this, traditional synthetic graphene from a lab is kind of like sticking two pieces of Velcro together. They hold, sure, but they're inherently separate entities forcing a connection, and they're relatively fragile.
That's a great analogy.
But this is where Gutierrez Guerrero's 3D Biogy solution flips the entire script. Instead of using a 1,000-degree furnace and toxic chemicals to force carbon atoms together from scratch, he just lets the coffee plant do it.
Right, because biology has already done the heavy lifting here. The wood and the roots of the coffee plant are made of natural polymers, lignin, and cellulose. And over months of slow growth, the plant naturally builds this highly intricate, three-dimensional, porous framework out of carbon. The atoms are already perfectly arranged.
So the process isn't about building graphene layer by layer. It's about taking this intricate wooden scaffolding and purifying it.
Yes, precisely.
Through a very specific stepped thermal process, they gently strip away the oxygen, the hydrogen, and, well, all the non-carbon elements. And what you're left with is a flawless carbon skeleton.
It's continuous structure. Because it wasn't violently ripped from a copper plate, the carbon atoms maintain perfect covalent bonds. They're actively sharing electrons in this uninterrupted network.
That's wild.
It is. And material scientists measure this structural perfection using a score called the Raman index, which essentially scans for those microfissures we mentioned earlier.
Right, and the numbers here in the thesis are wild. What does the Raman index look like for this coffee graphene?
It drops below 0.05. To put that in perspective, that indicates almost zero microscopic tearing.
Wow. A flawless, untorn atomic highway. And if this material provides a flawless highway for electrons, that directly solves the biggest thermodynamic crisis happening right now in our digital world.
Oh, the heat problem, absolutely.
Right, because if you're listening to this deep dive right now, your data is being processed somewhere in a massive data center. And globally, data centers consume roughly 460 terawatt hours of electricity annually.
It's a staggering amount of energy.
It is, but the crazy part is a massive chunk of that energy isn't even processing your emails or your streaming video. It's just powering industrial air conditioners to stop the servers from literally melting into slag.
And the culprit behind all that heat is the Joule effect. It's essentially electrical friction.
Okay.
In traditional silicon or copper circuits, as you push electrons through a wire to process data, they don't travel in a straight line. They bounce around.
Like a pinball machine.
Yeah, exactly.
Yeah.
They crash into the atomic vibrations of the material, and they crash into impurities. And every single microscopic collision releases kinetic energy, which we experience as heat.
But with 3D BioG, because that Raman structural perfection score is so incredible, those impurities and micro tears just aren't there to crash into.
Right. The electrons flow with virtually zero friction. To give you a sense of scale, scientists measure how freely electrons move using a metric called electron mobility. In typical silicon, it's fairly sluggish. But in this purified 3D BioG, the mobility skyrockets to between 10,000 and 50,000 square centimeters per volt second.
Okay, for anyone without a physics degree, how big of a jump is that?
It's huge. It is the equivalent of taking your car off a deeply rutted, muddy dirt road and dropping it onto a freshly paved, frictionless autobahn. The conductivity jumps exponentially.
That's incredible.
And because it's so perfect, it opens the door to something that sounds like pure science fiction, spintronics.
Oh man, I am obsessed with this concept. Let me try to explain it.
Go for it.
Imagine traditional electronics, so the phone or computer you're using right now. Imagine it as a delivery system. To send a piece of data, a 1 or a 0, you have to take an entire delivery truck, which is the electron, and physically drive it down a road from point A to point B.
Right.
You burn energy to accelerate, you burn energy to brake, you wear down the road, and you generate tons of heat. That is how all our current technology works. But spintronics...
It's completely different.
Exactly. You leave the delivery truck parked completely still in the driveway, and instead of moving it, you just spin it on its axis. If it spins to the right, the system reads a 1. If it spins to the left, the system reads a 0.
Yes, you encode information purely in the intrinsic angular momentum of the electron. It's spin.
Which is brilliant.
It really is, because you aren't forcing an electrical charge to physically plow through matter. So your energy consumption and your heat generation absolutely plummets. It's elegantly simple.
Okay, but if spintronics uses almost zero energy and generates no heat, I feel like Apple, Google, and Microsoft would have jumped on this yesterday. What is physically stopping them from doing this with our current silicon chips?
Well, it's the fundamental chemistry of silicon itself. Silicon contains a naturally occurring isotope known as silicon-29.
Okay.
And this specific isotope has an extra neutron in its nucleus. Now, that might sound harmless, but that extra neutron gives the nucleus a tiny net magnetic moment. It basically acts like a microscopic magnet.
Ah, like a magnetic pothole.
Exactly.
Yeah.
So when your parked electron is trying to maintain a steady, delicate spin to store your data, the ambient magnetic field of that silicon-29 pothole interferes with it.
It knocks it off balance.
Right, it bumps the electron, causing it to wobble and lose its orientation. This is known in quantum physics as a loss of spin coherence. The data instantly corrupts.
Wow. And to stop that from happening, to stop the ambient heat and those magnetic potholes from destroying the data, the quantum computing industry has resorted to extreme measures.
Very extreme.
Right now, to keep quantum processors stable, they have to encapsulate them in massive dilution refrigerators. We're talking $3 million multi-story machines that cool the processor down to fractions of a millikelvin. That is colder than the ambient temperature of deep space.
Yes, and achieving that temperature is a logistical nightmare. They rely on an incredibly rare isotope called helium-3. It is so scarce on Earth that the primary way we source it is by harvesting the radioactive decay of tritium from nuclear weapon arsenals.
Which is obviously not a scalable business model for consumer electronics.
Definitely not.
But this coffee-derived graphene changes the math entirely. Gutierrez-Gro's research shows that 3D BioG can maintain perfect spin coherence at 4 Kelvin.
Yes.
Now wait, hold on. Let me just play devil's advocate here for a second. 4 Kelvin is minus 269 degrees Celsius. That is still an absolute lethal deep freeze. Why is the industry calling this a massive revolution if the processor still needs to be frozen to that extreme?
It comes down to the physics of gases and the leap in infrastructure it allows. Moving the operational threshold from a fraction of a millikelvin up to 4 Kelvin is the difference between a bespoke science experiment and a scalable commercial industry.
How so?
Because 4 Kelvin happens to be the boiling point of standard helium-4.
Oh, wow. Wait, so we are talking about the normal helium you can just extract from natural gas.
Precisely. It's cheap, it's abundant, and it's the exact same cooling technology used to run standard MRI machines in hospitals all over the world.
So you don't need a $3 million nuclear-grade refrigerator anymore.
Nope. You drop your cooling costs down to a standard cryostat, which runs between $50,000 and $200,000.
That completely democratizes the technology.
If we connect this to the bigger picture, you're making things like MRAM commercially viable for everyday infrastructure.
What's MRAM?
MRAM is non-volatile magnetic memory, where your devices never lose their data when the power cuts out, all because the spin state is preserved.
It is wild to think that comes from a coffee plant. But if we pull back from the quantum level for a minute, the atomic perfection of this material doesn't just revolutionize the invisible subatomic world. These exact same properties scale up to fundamentally alter heavy industry.
They do.
Because if this continuous carbon scaffolding is perfectly unbroken, it is unbelievably strong.
Yeah, the mechanical analysis of the 3D BioG reveals a Young's modulus of roughly 1 terapascal.
Okay, give me a comparison for that. Like, how strong is 1 terapascal?
Well, let's look at the heavy structural steel used to build massive suspension bridges. That steel has a Young's modulus of about 0.2 terapascals.
Oh, wow.
So this purified carbon skeleton from a coffee shrub is roughly 5 times stiffer than the steel holding up the Golden Gate Bridge.
Okay, physics question, though. If it is 5 times stiffer than steel, shouldn't it be incredibly brittle? Like if you take a sheet of glass, which is very rigid, and you try to bend it, it doesn't flex. It instantly shatters into a million pieces.
That's a great point, and that's how conventional rigid materials behave, yes. Yeah. But we have to remember why glass shatters.
Okay.
When you apply bending force to glass, that mechanical stress travels through the material looking for the weakest points. You know, the microscopic cracks and fissures. It concentrates all its kinetic energy into those tiny defects, ripping the material apart instantly from the inside out.
Got it.
But 3D BioG doesn't have microfissures. It has that flawless, continuous covalent bonding.
Right, because it wasn't ripped off a copper plate.
Exactly. Because there are no microscopic defects for the stress to concentrate on, the physical force is distributed perfectly across the entire atomic network. The result is a material stiffer than bridge steel that can actually stretch and bend up to 30%, almost like a rubber band, without breaking.
That's hard to wrap my head around.
And crucially, it does this without losing its electrical conductivity.
Which paves the way for what the industry calls skin electronics. You could have lightweight spacesuits woven with biometric circuits and radiation shielding built right into the flexible fabric, drastically cutting down on weight.
Exactly.
But bringing it back down to Earth, it completely solves the massive weight issue of electric vehicles. If you look at an electric city bus today, heavy lithium batteries make them highly inefficient. It's this vicious cycle where the bus is wasting a huge amount of its own energy just to haul around the heavy metals required to power it.
Yeah, it's just dead weight.
Mhm.
But with 3D Bio-G, the physical architecture of the vehicle itself can change. Because the material is structural and conductive, you can build the actual chassis and the body panels of the bus out of this biogenic graphene.
Wow.
You're turning the skeleton of the bus into a structural supercapacitor. The chassis literally becomes the battery.
So how much weight are we actually saving if we remove the traditional lithium battery bank and just use the frame?
It drops the weight of a standard urban electric bus from 14,000 kilograms down to just 8,000 kilograms.
That is massive.
You are stripping away 6 tons of dead weight.
And because it is a supercapacitor, it stores energy entirely differently than the lithium-ion battery in your phone, right?
It does. Traditional batteries rely on slow, internal chemical reactions. You have lithium ions physically forcing their way into the electrode structure and then back out.
Mhm.
But a supercapacitor stores energy electrostatically in its 3D porous network.
Right. The best way I've heard this explained is to imagine rubbing a balloon on your hair. That static cling you get is electrostatic energy. Now imagine a highly conductive sponge the size of a bus holding onto that static energy on a massive, highly efficient scale.
That's a perfect way to visualize it.
Yeah.
And that electrostatic storage means there is no complex chemistry slowing the charge down.
Okay.
And because the electrons move without friction, you can charge that entire bus chassis in 30 to 45 seconds.
No way, really?
Yeah, that is the exact amount of time the bus spends at a stop letting passengers on and off.
So it literally charges while people are boarding. That's incredible. And crucially, because there are no volatile chemical liquids or lithium involved, there's absolutely zero risk of thermal runaway fires.
Which is a huge safety leak.
Okay, so we have a material that is resilient enough for the vacuum of space, stiff enough for the chassis of a city bus, and conductive enough for quantum computing. But if this material is so chemically pure that it prevents a bus battery from catching fire, well, that exact same purity solves an even bigger problem inside the human body.
Ah, yes. The biological interface.
Yeah.
Historically, trying to put nanotechnology into the human body has been a disaster of toxicity.
Right.
If you look at traditional neuroprosthetics, like the brain implants being developed to help paralyzed patients, they have typically relied on that old synthetic CVD graphene. And we know that manufacturing process leaves behind toxic chemical residues.
Stuff like solvents, right?
Exactly, solvents like hydrazine and benzene.
And the human immune system is a ruthless pattern recognition machine. When you insert a synthetic, chemically tainted wire into delicate tissue like the brain, the body's macrophages, which are basically the immune system's cleanup crew, they detect the foreign toxins immediately.
And they do not like it.
No, they don't. It triggers a massive inflammatory response known as cytotoxicity. The immune system attacks the implant.
And when the body realizes it can't kill a piece of metal, it just builds a wall around it. It encases the implant in dense, thick scar tissue until the electrode is completely isolated and physically unable to communicate with the brain.
But 3D Bio-G requires absolutely zero toxic solvents during its creation. It is entirely clean. And more profoundly, its physical topography is completely different. The cellular architecture of this purified plant matter flawlessly mimics the dimensions and the structure of the human extracellular matrix.
Yes, the structural similarity is key.
Right. And here's where it gets really incredible. The material is essentially speaking the body's native biological language. When it's implanted, the immune cells don't see a flat, toxic, metallic invader. They see a friendly, organic scaffolding that looks just like the cellular neighborhood they grew up in.
When you look at the clinical observations of this, it is remarkable. Because it mimics the biological environment so perfectly, the immune response is almost entirely suppressed.
Oh, wow.
Neurons and nerve endings don't run from it. They actively grow into it. They intertwine with the graphene's porous network, creating a flawless, long-lasting brain-computer interface that doesn't trigger scarring or degrade over time.
It is a total paradigm shift, and honestly, a breakthrough. This vast spanning quantum computing, heavy transport, and human biology inevitably triggers a massive economic and geopolitical earthquake.
It absolutely does. It forces a transition to what economists are calling bioshoring.
Bioshoring. Okay, what does that mean exactly?
Well, for centuries, the global economy has been defined by extractivism. The global north extracts critical minerals, like the cobalt and lithium, powering the smartphone in your pocket right now from the global south.
Right.
This leaves behind profound ecological devastation while the wealth flows outward. But 3D BioG flips that dynamic entirely.
Because it means the phone in your pocket tomorrow might be powered by a material grown on a farm. I mean, in Costa Rica alone, there are 150,000 tons of coffee pruning waste generated every single year. Material that used to just rot in the fields is now the literal foundation for the next century of computing.
And Gutierrez Guerrero has even developed a system to use this technology for environmental protection. It's called the Phyton 3D BioG cell.
Right, we looked at this in the source text.
Yes, this is a real-time monitoring technology built from the biogenic graphene, designed to detect chemical and radioactive spills in the soil. It is currently being applied to monitor ecological damage from activities like illegal gold mining in northern Costa Rica.
And looking strictly at the capabilities of the tech here, this system sends real-time alerts directly to the cell phones of local communities. It provides irrefutable, hard data that can be used internationally to penalize polluting corporations that previously evaded oversight.
It's a powerful tool.
It puts actionable data into the hands of the people actually living on the land. So what does this all mean for you? It means the economy of this future might not be dug out of a mine. Financial projections suggest this convergence of nanomaterials could create a $2.8 trillion market by 2035, a market relying entirely on sweeping up farm clippings.
What's fascinating here is how the strict laws of thermodynamics and quantum physics are actively forcing the world into a circular, regenerative economy.
Yeah.
Think about the current tech infrastructure. A modern silicon microchip megafactory can cost upward of $20 billion to build.
Just massive investment.
Right. If computing transitions to biogenic graphene spintronics, those massive, energy-hungry silicon facilities risk becoming stranded assets, essentially obsolete overnight.
Which brings us to the ultimate philosophical takeaway of this entire journey. We started in the damp, muddy soil of a coffee farm and ended up discussing interstellar spacesuits, quantum spin, and brain interfaces.
It is a profound lesson in scientific humility. For decades, humanity believed that dominating matter required brute force. Extreme heat, extreme pressure, toxic chemicals.
Yeah, beating it into submission.
Exactly. But the real quantum leap didn't happen until we stopped trying to force nature to our will and simply read the molecular templates that biology spent hundreds of millions of years perfecting.
It's beautiful, really.
Gutierrez Guerrero actually has a quote in his thesis that captures this perfectly. He wrote, "Forge the sciences of the future with hands in the dirt, but looking to the stars. The true quantum leap of computing doesn't lie in creating an artificial mind, but in transforming ourselves into the conscious link of a biosphere that has been waiting eons to be heard."
It fundamentally changes our relationship with the natural world. And it leaves me with this one thought I just can't shake.
What's that?
If a simple agricultural shrub, a coffee plant we pass in the fields every day, silently held the master blueprint for the global quantum era hidden inside its woody anatomy, what other hyper-technological templates are hiding in plain sight right now?
Oh, that's a great question.
Could the exact molecular architecture needed to survive interstellar radiation be coded into a random mushroom growing in the woods? Could the cure for cellular aging be waiting in a weed pushing up through the cracks in your sidewalk, just waiting for us to find the humility to drop to our knees and read it? Thank you so much for joining us on this deep dive.
Thank you for listening. Next time you see that mist rolling over the mountains or a weed growing in the pavement, maybe take a closer look.